5? No. What about 4?
Yes.
Oh, look at you. Really?
Yes.
Yeah. Every one of those loops is automatically a two-way street between the element and itself. I don't think people talk this way, but you could look in the mirror in the morning. I'm your friend. Like as you're on your way to school. And then you say, I'm your friend too. Okay, let's go. You go to school or whatever. So that's kind of what that one is. How about 3?
No. Oh wait, yeah.
Oh wait.
Oh my god.
Oh my god.
Yeah.
Yes. If anyone is related to somebody else, does the other one repay the favor? And the answer is yes.
I thought it's a two-way street.
It is a two-way street. It says, which one are we on? This one?
Yes.
Are we on 3?
Yeah. 3.
3 says, so there's no street going this way. If there was a street going this way, then we say, okay, you gotta come back. But this one says, I'm gonna relate 1 related to 1. And then I try to say it the other way around, and I say, does that mean 1 is related to 1? And the answer is yes. So that one passes the symmetry test. 2 for the same reason.
Yeah.
Okay. And then 1.
Yes.
No.
Ooh, there's a
No.
little more heated.
Yes.
Yes.
Yeah, because
No.
the answer
Goes
is
like
one.
away. Yeah. No. Yeah. I could see a person saying no because there's no streets at all, let alone two-way streets. However, the description of symmetry is if blah blah blah, then blah blah blah. The if part does not happen. The if part is false.
Back to logic.
We're going all the way back to chapter 1, the cycle of life in math. So if the if part is false, the thing satisfies the property. The entire statement is true. So even though nobody's related and it's kind of a boring, empty relation, we say, well, you got in on a technicality, you're symmetric. Reflexive, why I started with reflexive is a little clearer because it's something affirmative that has to happen. In order for a relation to be reflexive, everybody has to be related to themselves. So you have to see the relationship. Symmetry is not that. Symmetry says if, then. And the part that's tricky is if the if part doesn't happen, we kind of want to rule the thing out, but no, it's still good. Oh yeah, that one right too. I can run back. All right, is this fun? See how you can look like a genius sitting in a coffee shop with just a few dots on your paper and circles, and then you're thinking very deeply, and the person asks you what are you doing, and you say you wouldn't understand. You look like a genius, and you are. I don't know about genius, but you're pretty smart. Okay, so there's 2 more properties that we look for. I sometimes do this on Bart just so that I will look smart. I'm not even doing anything. I'm just throwing circles and arrows. Okay, let me give you the 3rd property that was related to that mod thing we were doing on Thursday. I'm switching colors for no reason. So this is transitive. And somebody told me today, who was this? This was Mr. Simon, who teaches calculus right now. He's teaching calculus out of the new calculus book, which has a lot of mistakes or bad problems in it. And his class didn't go well, and a student was upset and was angry or whatever, annoyed. And Mr. Simon said to the student, he said the transitive property. He said, all right, he says to the guy, you're not mad at me. He said to the guy, he said, I'm angry or irritated, maybe he said, I'm irritated with our textbook. You are irritated with me.
Therefore.
Therefore, you're actually irritated with the textbook. And he even used the word transitive, though the student did not. So that's a transitive property. There's sort of a two-way or a two-step street for the relation, and then there's a direct path. Okay, so transitive for all A, B, and C in the set A. And this one also starts with the word if. So this is if A is related to B. So this could be like student annoyed with teacher and teacher annoyed with textbook,
Then A is related to C.
then A is related to C. So that's transitive property. So that, when you see that in a relation, it's not always, we're not always gonna be in a situation where we're looking at a digraph and trying to check for this. But how I think of it is, graph-wise, I think if there's a two-step path from A to C, is there a direct path from A to C? So this, A related to B, that would mean, I'll draw a little example. These are the ones of these that have the transitive property. It's trivial because we don't have enough points in the mix. But let me go A, B, C. So let me write down what I said. So if A is related to B and B is related to C, that means there's a two-step path, I will say, from A to C. The transitive property says if there's a two-step path from A to C,
There's a one-step path.
then there's also a direct path. And some relations have that. I think the kind of relations you've encountered this in your previous math classes. Oh yeah, like less than. Less than is a relation between numbers. If 3 is less than 5 and 5 is less than 9, then 3 is less than 9. That's a transitive relation. How about the friendship relation? If A is friends with B and B is friends with C, then
Doesn't.
no, you're all shaking your head like you know somebody specific in your mind. Yeah, that doesn't work. So for us, I mean, I don't know that these things are good or bad, but transitive is often what we're looking for. When we were getting those, that digraph on Thursday to clump up into clumps, it was because the transitive property was working. I'll say, and I'll show you another example of that. All right.
The comparison test is one for calculus.
Kind of, because it's less than generally. If you're thinking about a series converging, you're thinking the limit is a finite thing. Yeah. All right, these are going to be kind of stupid because we don't actually have any situation with 3 individual points. These might actually all be transitive as it stands. First one is a transitive.
Yes.
Okay, you guys you're totally accepting that there's nothing to make it fail. Okay, great. So that relation is symmetric and transitive. Second one, there's only one arrow there. If I tried to run through the transitive, I would say, well, 0 is related to 0, and 0 is related to 0, so 0 must be related to 0.
Yes.
Yeah. Boring, but yes. Same with R3. So these first 3 are all transitive. How about this one? Yeah. There's nowhere that's going to cause us to break the transitivity rule. So on each of these vertices in the graph, we're going to still be doing that same trivial version of transitivity as we did here. The only way here we could say A is related to B and B is related to C is that A and B and therefore C have to be the same number. So that one also transitive. How about R5? If there's a two-way street or a two-step path, there needs to be a direct path. If there's a two-step path, if there is no two-step path,
So true.
so true, all right. You guys you're so mature. At the beginning of the semester, you refused to accept that. That's great, you've shown progress. I wish I could just say the class is over and y'all give an A.
You can.
If I could say that, then
But you can't.
my
so
boss
it's
won't
true.
let me. How about this one? 7.
Yeah.
Yes.
Yeah.
Yes, yes,
So the only way to get a two-step path from 0 to 1 is to go 1,
yes.
2,
Or just directly.
and then there's the direct path. So also transitive. Darn it, did I give us only transitive? With only 2 points, it's hard not to. And that
Yeah.
one is 2. That has everything, so this is good.
Can we conclude that if the set has, or,
If
Yeah,
there's two,
two is
like
good.
2 points.
because then there's no third one to compare with to see it. That's a theorem right there.
No, that's an excellent question. So remember, this is only half of the relations that you're gonna see in your homework problem. Let me give you like number 9, which is not gonna be transitive. Though I admire that you're trying to see the larger principle. So the time students normally miss this one is when there's something like this in the graph somewhere. So here I would say 0 is related to 1. I see the arrow clearly. And 1 is related to 0. So 0 goes to 1 and 1 goes to 0. But 0 would have had to be related to itself. So the A and the C are actually the same value as each other. So that relation is not transitive.
Did you explain it again?
Say that again?
Did you explain it again?
Yes. So here I'll say 0 is related to 1. The arrow points that way. And 1 is related to 0. And I'm thinking transitive. So I'm thinking A, B, and then B, C. So A, B, B, C. So we're checking, is 0 related to 0? And the answer is no. This is how math is later. It's not all that crazy multiple integration.
I still don't get it.
Optimization, it's just dots on a paper. So A is related to B. B is related to element C. But A is not related to C. So we're checking, I should have written it this way. So we're trying to check this, but that doesn't happen. And as soon as there's one spot in the graph where that transitive condition is not satisfied, even if the whole rest of the diagram makes it look transitive, one failure is it makes the whole thing fail.
If this is like in a condition that you said you're my friend, like A is a friend of B, but then B is a friend of C,
But A not.
and then they don't, so
Yes.
that doesn't mean A and C are friends.
Correct. And then this version would be a little ridiculous, but okay, A is a friend of B, and B is a friend of A, but A is not a friend of themselves.
So sad. Damn.
I don't know why.
Just learn to love yourself.
Are you your friend?
I personally am not, but I don't have a lot of these two ways.
Is it lambda versus hammer? Or lambda related to hammer and hammer related to lambda?
I hate the hammer.
What?
All right,
the
is this
best one.
wacky?
But it's kind of weird though.
No, I don't know who they are. Sorry. you trying to be my friend in the friend relation?
What was reflexive?
Okay, let me mention one more property and then I'll try to describe there's two different groupings of these properties that we often look at. And, one of them is the one that causes the set A to break into clumps. And it's actually the combo that involves reflexive, symmetric, transitive. But since I'm gonna have to erase these all shortly, I'll leave them up for a couple more minutes. The fourth property or potential property the relation can have, your book is gonna mention a couple others, but these are kind of the main ones. So reflexive, or testing a relation for reflexivity, symmetric or symmetry, transitive or transitivity. And then the fourth one I'll say is, it's called anti-symmetric. And this one has a funny way that it's worded. So this way, this one is almost trying to say, if you're related to me, I'm not gonna be related to you. It's kind of the opposite of making a two-way street.
So both arrows point one way, kinda?
Is it like
Well,
the,
we would only show one arrow if it's pointing.
is
to
it like
just
the
a-
example that you said that I'm older than you, but you're not older than that person, so therefore it doesn't go back?
It only uses two elements, so
Right.
there's not a compound
Okay.
relation.
So it's 600.
So what this one has kind of a funny, just for fine print reasons, we say it in a funny way. It kind of is gonna try to say this: the only two-way streets are loops. The only possible two-way street in the graph is if an element is related to itself. So how I think of it is, if A is related to B, then B is not related to A. That's how I think of it, but that's not what it is. So what antisymmetric is if A is related to B and B is related to A, so this is an exact violation of what I just said. I just said if A is related to B, then B is definitely not related to A. But for various reasons, we leave open one exception to that. The only time we'll allow a mutual friendship society or whatever is if A and B are the same point as each other, and the element is actually just related to itself. So it's a very awkward way that it's said, and believe me, I've spent years in grad school trying to come up with there's no better way to say this than this. So it's, if A is related to B and B is related to A, then A equals B. Casually, you can say there's no two-way streets except loops. Wacky, yeah? And the things that you know that are in this category are things like less than or equal. So what if I said, say I had two sisters with the same IQ. I have no idea what their IQs are. And I said, what if I said, Janet's IQ is less than or equal to Susan's? And then I said, and Susan's IQ is less than or equal to Janet's. So Janet's IQ less than or equal to Susan. Susan's IQ less than or equal to Janet. They have equal IQs. So that would be anti-symmetric. I'm gonna tell them that next time I see that.
I read in the book one of the problems, and it said, it kind of simplified it. It said that a relation is antisymmetric if you find a pair AB such that it is in the relation but BA is not.
You're saying if it's not symmetric, correct?
Right.
Yes.
Yeah, is that antisymmetric? So,
No. Antisymmetric is, there's never any two-way streets. So symmetric is all the streets have to be two-way streets. Anti-symmetric is no two-way streets except for loops. So the description you just gave was this. AB is in the relation, but BA is not. So that's not symmetric. All right. Isn't this weird math? I don't really see you guys writing a lot down. What are you gonna write? A bunch of zeros and ones with arrows?
Yeah.
So I'm gonna try to cram down your brain.
Put it in the file on my brain.
I'll make this be related to your brain. So whatever this means, but the interesting combinations of properties, I think the last problem that we did on Thursday was I had given us some set of numbers, and I might have just given us the set of numbers 1 through 10 or something like that. And I made us do a relation using mod. Remember that one?
Yeah.
That was a famous example, except for the set I picked. So I'm gonna write down the beginnings. What time does our class end?
18 minutes.
18 minutes. Really?
50.
17.
Okay. I let my early class go 15 minutes early by accident. I don't want you to kick me.
Wait, 15 or 15?
15?
Oh,
No.
right now. Right now.
18
Okay.
or 17.
So let me start. I'll call this VIE, very important example. I'll give us the set A, and I'm gonna give us two different relations on this set A,
I think I'll-
and we'll see how far we get today. Where I was hoping we might try to check all four of those properties for both of these relations. And then on Thursday, I was gonna say more about that, but we'll see how far we get today. So this is a very important example. I'll give us for the set A. I could give us the numbers 1 through 10, but that's typically not how these relations arise. I'm gonna pick all the numbers that go into 24 evenly. So I'll say this is all of the positive